The next talk is by Diaconescu, and he talks about vertical Thomas invariant and modular forms.
Okay, thank you very much. And let me start by saying that it's really a great honor for me to speak at this conference. Because Ron has been a very good friend for many years, and he has, together with Tony, he has pretty much being a mentor for me in mathematics. They taught me pretty much most of the math I know, and I wanted to thank him for all the help he provided and all the papers we wrote together, and I hope there's going to be many more to come. And yeah, so let me start. Oh, and I should say happy birthday. So this is about vertical Donaldson-Thomas invariants and modular forms. So this is work that's finished together with very big collaboration. So with Vincent Bouchard, so pretty much the Alberta group, Thomas Kreutzig, Chuck Doran, Alan Quigley, and somebody not from Alberta, Arton Jashmani, who is here in the audience. And I should say that actually this is somehow generalized as some previous results obtained by Arton and with Amin Golancourt. I'll explain more about it. Okay, so what's the setup? So the setup is we're looking at X, which is a smooth projective Calabi threshold. Well, what else? This is pretty much all physicists know about. It has to be Calabi threshold. But I want to look at X very quickly to map down to P1, which makes X the total space of a K3 pencil. So X is end up being the total space of a K3 pencil, which means that the fibers are K3 surfaces, the fibers of pi, and generically they are smooth, so I have generically smooth fibers. And I allow, of course, singular fibers, but very controlled singularity. So the bad fibers are going to be only reduced, irreducible, nodal surfaces, by which I mean really simple nodal singularities. Sum of x squared equals 0. That's all we allow for now. I mean, there might be generalizations down the road, but for now. And then let me look at Kx is the K theory of x grown to the group of X mod, numerical equivalence. So this is some kind of, physicists think of it some kind of group of Abelian group of charges, of GPS states. And we call gamma in here, this is going to be a vertical class. If gamma is the class of some sheaf E, where E is supported, is a coherent sheaf on X, which is supported on the K3 fibers. Okay, so that's a vertical class for me in this talk. And then given this, what we're going to study is Donaldson-Thomas invariants. Namely, so we have, well, perhaps I should, well, let's take omega to be a Carlo form, very ample divisor on X, the polarization.
Will you work in billions just a coherent sheaf?
Well, here I don't care because I'm looking at, this is just the equivalence class in the Grothendieck group. But well, that's what I'm going to say right now. I mean, what am I counting? So the Donaldson-Thomas invariants, dt omega of x gamma, are going to be, these are counting omega semi-stable sheaves. So not this answers the question. I don't mean complexes. I mean really mean sheaves on X in class gamma. And omega semi-stable, this means exactly omega semi-stable. So just it is. I'm not going to keep saying this, but this is what it is. So this is the kind of objects we want. Now, what are these? These are, of course, some kind of virtual numbers. So if gamma is a primitive class, you don't have to deal with semi-stable objects. So then these guys are going to be virtual cycle invariants. And the integral, this was they were constructed by Richard Thomas in his thesis, essentially. If gamma is not primitive, so you might have, or you will have in general semi-stables, you have to employ a more general theory to count such objects. So maybe I should say, in general, what we want, so we can have these are virtual cycle invariants. If I don't have semi-stable, so that's constructed by Richard Thomas. And then we have more generally, and they are integral. So more generally, we can have some, we really have rational invariants. And those are constructed, they really, well, they are really a special, very special case of the work of Kontsevich and Soberman. And also Joyce and Song. And well, perhaps I should mention that. So from here we can extract. There is a conjectural Monte Carlo formula, which says that all these rational invariants can be written as follows. So sum over integers that divide gamma, 1 over k squared omega gamma over k, and this would be integer. These are some so-called, this is really what in physics is called the BPS counting invariants for this particular problem. They are integral invariants, so these are rational. But these are going to be the sort of the main characters of this work. For some reason, it turns out that the modular forms, I mean, in order to exhibit the modularity properties of this theory, you have to look at the rational invariant. Okay, so basically what we're going to do with this, we make a generating function, of course, or a partition function, the way physicists like to think about it. And we want to, well, first compute it explicitly if we can, and then prove that it has certain modularity properties which are predicted in the physics literature. So let me see. So we make a generating function. We call it z vertical dt. For now, very schematic. I'm going to be more precise about this. Some generating function. And we want to compute it and prove that it has modular properties. So I should say the goal is to compute it and prove modularity. So I should say at this point, I should mention that there are previous results. So this was in some examples, this program was completed by let's say Polanco and Sheshmani. So previous results in some cases. And also, well, and I should probably mention that if there is work done by physicists, the predictions that the modularity predictions really follow from modularity, they really follow from work of Denef and Moore, and also Gaiolo, Strominger, and In. So these are words. So they predicted modularity based on all sorts of physics arguments that I'm gonna skip. And there are some previous results, basically for smooth K3 pencils and all stable objects, and also for rampant objects on nodal K3 pencils and so on. So this is what we're trying to do is kind of obtain general results for all, for arbitrary the class is gamma on nodal cases. All right, so now to state these results, I'm going to have to say a few words about the notion that was used in this context, in the context of the Gromov-Witten theory of such threefolds, which is a lattice polarization. So I'm going to, which is some notion that, well, I mean, it's a fairly, it's standard in mathematics to some extent, but it's the way I'm going to, so lattice polarized K3 pencils. Now, I'm certainly not an expert in any of this stuff, but so what this is and probably there are many ways to think about this or to define this, but the definition I'm going to use in this talk is the one used also by Merle and Penner-Rekande, who studied the vertical Gromov-Witten theory of such pencils, of K3 pencils. And actually their work will be very important for us later on. But for now, again, I'm not going to give you the very strict technical definition. I'm going to kind of try to explain what we really want, which are the main ingredients in a more sort of informal way. So informally, what I really want, and perhaps it's really stronger, it's somewhat stronger than this, but in generic situations it's good enough. So what we want the Picard group of X to split as some kind of lattice lambda plus a one-dimensional lattice generated by the K3 fiber class. So this is the K3 fiber class. So you want this to split like this. And lambda, on the other hand, this is it's a lattice which is actually, lambda is the sublattice of what I call lambda K3, which is just the middle cohomology lattice of a smooth generic K3 surface. And we want, if you take the intersection form, that the natural intersection form leading there restricts to, so the intersection form restricts to bilinear form of signature 1, rank of lambda minus 1. Okay, so that's sort of the discrete data of the theory. We want this to happen. And also, so we have this. And we also, I want the Picard group of a sufficiently generic, of a generic K3 fiber to be basically isomorphic to lambda by restriction. So this is for sufficiently generic fibers, XP, with P in P1. Now, sufficiently generic doesn't just mean that you stay away from the singular locus. Of course, we stay away from the singular locus, but there are also interesting smooth special fibers, which are the so-called Northern lattice fibers. I'm going to say a few words about that, where this condition is not satisfied and it jumps in a very interesting way. Okay, so that's what we want. And now if you have this, then in quantum duality you can show that the if you take the if you call, let's say, if you take if h lower 2 of x and let's say, I'm going to assume there is no torsion. I'm going to make my life easy. If I define this to be the kernel of pi lowest star on H2 of x. So these are some lattice of vertical curve classes, right? So we have vertical curve classes. Then this guy here ends up being isomorphic to lambda duo by Poincare duality. And notice that throughout this talk I'm going to implicitly use a lot the fact that lambda is naturally embedded in here using the bilinear form. So just a remark, keep in mind for later on, because I'm not going to keep repeating this. Lambda sits inside here as via the bilinear form. And it's very important that, in fact, in the very interesting situations, this is not isomorphism. This is just an improvement. All right, so now if we take E to be a vertical shift, which means a coherent shift supported on the K3 fibers, then it's numerical invariants are going to be of the following form. Term 1 of E is just the multiple of the K3 fiber class. Term 2 of E is going to be some element D in lambda dual for this identification here. And then term 3, well, term 3 is whatever it is. It ends up being an integer, which is more convenient to write as minus n. Term 3 of the minus n here in Z. So I'm just going to use this. This is just conventions, but it makes the formula much nicer. Good. So now the numerical invariants are going to be written as gamma equals R dn. So it belongs obviously to Z cross lambda dual cross E. All right, so those are my numerical invariants. And now let me be more precise. So let me just be more precise about the construction of the generating function of Donaldson-Thomas invariants. So now the Donaldson-Thomas invariants, remember, I'm going to write them. Well, they're not the gamma. These are they are rational numbers, and apparently they depend on the polarization omega. But in fact, they don't. If you use the word-crossing formula, for example, of Kontsevich and Soberman, you can immediately see that there is no dependence on omega. So there's no chamber structure for the invariants. I mean, there might be a chamber structure for the moduli spaces, but I don't care about that. I'm not caring about the numbers, the virtual numbers. So there is no omega here. We can ignore it. Forget it. All right. So then I make a generating function, z dt of x. No, I'm sorry. Apologize. So for fixed R in Z positive and a D in lambda dual, I'm going to define z dt of x rd to be a sum over all n in Z q to the n plus d squared over 2r minus r dt omega of r dn. Now, what's this squared? Well, let's think about it. Lambda, it comes with an integral form, with a nice symmetric integral and so on, bilinear form, which extends by collinearity to lambda dual. Okay, so remember that this is contained, but lambda dual in turn is containing lambda tensor q. So we can inherit some bilinear form, and that's what gives you this square here. Except that it's q valid, it's no longer z valid. Okay, so this is a construction. Why is this? Actually, there is a reason for choosing the exponent this way, and that comes from physics, and I'm not going to explain it. But the important observation here is that once you define it this way, you can, the important property here is that I can shift d plus multiples of elements in lambda, okay, and I don't do anything to the generating function. It's preserved under such shifts. And that really comes from, if you try to track where this comes from, it comes from the fact that the moduli spaces are invariant by under tensoring by line bundles on X. So that's really where it comes from. But this is an important fact for us. It's sort of very obvious, but it's important. So because of that reason, we can write, we don't have to think about this D, because this is invariant, I'm going to just, sorry, this is an abuser notation, but couldn't come up with anything better, I guess. I'm just going to write it like this. Delta, where delta is an element, and lambda dual mod R lambda. Okay, so D is not really, well, it's lambda dual because it's invariant under such. Okay. So now the goal is, as I said, I want to compute and find an explicit formula for this and prove that it has interesting modular properties. But in order to do that, in order to even write down the formula, I have to say a bit more. I have to go to another piece of background, which is another glitch that's in loci and numbers. At least I have to say a few words to fix the notation. Of course, I can rely on the audience, because many people know much more about it than I do. But in order to just fix the notation, let me just say a few words about this. Again, pretty much everything I know about this is it's stuff that I learned from the paper of Diaconescu and Rocco. So again, following Malik and Van. So again, I'm going to be very informal. I don't want to get into very technical stuff. The first thing to do, there is some level of technical detail you have to get into, because these guys are normally rigorously defined only for smooth pencils. So we want to have a smooth pencil. So we have to do something to the nodal fibers. So what they did is the following. So the idea is we want to construct and some kind of auxiliary smooth K3 pencil. And the way to do that is to change base. So let me just explain quickly their construction. We changed base for the K3 vibration. So what we do, so our K3 vibration started out like this. We want to change base here. Take a double cover. So I'm going to call this X sigma. We change base. So how is this chosen? Well, if this is P1, and these are the locations of the singular fibers. Okay, so those are the locations of singular fibers. Let me assume that, for example, there is an even number of them. If not, I have to add another base point. So this is really nothing else but a technicality. So then I take a double cover which is branched precisely here at each of these points. Sorry, my picture is not that good, but okay, you get the picture. This is sigma. So it branched over each of the locations of the singular fibers. So what you end up getting, this is going to be a nodal threefold. So this is going to have ODPs, isolated ODPs, and what you want to do is resolve them. And unfortunately, you can't do that in the projective category. So there is a non-projective, in general, is non-projective resolution, X twiddle for X sigma, which resolves the ordinary double points, and it's of course fibered over sigma. So there's a pi twiddle map here, and this here ends up being a smooth K3 pencil. Even if it's not projective, it's a smooth pencil of algebraic projective K3 surfaces. So pi twiddle, it's a smooth algebraic K3 pencil. If you look at it 5 by 5, what this construction does is basically it provides an embedded resolution of the singular fibers if you trace it through this construction locally. So each singular fiber here has been automatically replaced by its canonical relative resolution in an embedded way. And now that I have a smooth K3 pencil, even if it's not projected, that's not really important. I can define nonetheless numbers. So we have, let me call NL twiddle HD. So H is an integer. D is an element of the dual lattice. So this is informally again. Let me put in quotation marks. It's the number of vertical curves on X, curve classes. Let's be more classes, beta on X, such that beta squared is 2h minus 2, and beta dot alpha is d of alpha for all alpha in lambda. So we specify the degree and the self-intersection in fiber-wise self-intersection. This is fiber-wise, with the vertical curve classes. Well, the way to count them, well, you can count them, but you have to be careful. What this really means, this number is really computed by intersection theory. So it's not it's not a naive count. I'm not going to explain in detail how it's done. As I said, it's explained in a lot of detail by Malik and Conde. But you need to use intersection theory and possibly even excess intersection theory to really define these numbers. But the important thing is that they are well defined once you have a smooth pencil. And you see that they encode precisely the point. The interesting action happens at those points in the base where you have extra curve classes. So remember that we had something like peak xp was lambda for generic p, for sufficiently generic p. But the interesting points are those where this fails and the Picard group is larger, it jumps, the rank jumps, and then you have to control in which way it jumps. So these numbers are incarnation of that. And now, the really interesting, the really deep stuff about these numbers is that they are basically coefficients of vector value modular forms. So this follows from the work of Borchers and Kudla and Nielsen. The statement is that N, L, HD are somehow related. I'm going to explain in more detail the coefficients of vector valued modular forms. So we get interesting arithmetic properties here. So the statement would be the following. So there exists, there are a few things to say. So how do I want to say that in which order? There exists some so if I'm given this lattice lambda with the intersection form, restrictions the intersection form, from here I can determine a representation, rho lambda, of a metaplectic cover of SL2Z into the endomorphisms of the linear span of lambda mod lambda dual mod lambda. So let me see first what I'm saying before I go on. This is a finite abelian group, right? I take the quotient of lambda dual mod lambda, I get a finite abelian group, and I take its linear span, and the statement is there is a canonical representation of a metaplectic cover of SL2Z. So NP to Z, it's a 2-to-1 cover of SL2Z. Again, I'm not going to get into details unless I'm specifically asked to. There is some canonical metaplectic cover, and there is a representation like this. And this is actually an old construction. This goes back to Vail. It's known now that it's a Vail representation. It's not really recent. It's a canonical representation like this. And then what Borchers and Kudla and Nielsen proved is that there exists a vector value modular form of. So now there exists. I'm going to call it phi twiddle. Let me see. Well, it's in series 1 over 2m, where m is the cardinality of lambda with the word mod lambda. So there is this vector value modular form with values in rho lambda and weight W equals 11 minus the rank of lambda over 2, such that NLHD, so these are the numbers here that count these curves, are related to the coefficients, the Fourier coefficients of phi twiddle in the following way. This is phi twiddle coefficient of order d squared over 2 minus h plus 1. Delta, where delta is just the class of the equivalence class of the in the cosine. And what this is, oh sorry, I don't need two brackets, I need only one. This is just the coefficient of phi twiddle of this order. As you see, this is a rational number, so that's why this is actually has a Fourier expansion into the fractional powers of the modular parameter, exponential of the modular parameter. So this is a very deep result concerning polarized lattice polarized three pencils. And so we get this vector value modular form, and then I can finally state one of the main results in our paper, which is what are the results? Well, I should say, well, results. Well, I won't state that it's a theorem. I mean, although we do have. Well, I explain in what sense this is almost a theorem, but let me just call them, well, what we claim we prove to some extent. Okay, so we want to say that ZBT of x r delta. It's the first claim. It's a very explicit form for the series, which is going to be given like this. It's 1 over 2r squared, sum over k and l integers, k and l greater or equal to 1, r equals kl, sum over s equals 0, l minus 1, of l, so there's a factor l here, I should put it there, or maybe here, it doesn't matter. And then the summands are phi twiddle, delta, no, not delta, sorry. Just write it and then I'll explain. So what's written here? So remember, r as it's just a positive integer. This is the rank of the sheets we're talking about. Delta, rank over the support. Delta is a constant in here. It's in here, r lambda. And delta 1 for me, so here's a notation, delta square 1 is just the projection, the natural projection onto the Gaussian lambda dual mod lambda. So there is an obvious natural projection map there, so I'm going to call delta 1 is the image. So anyway, so this is one of the claims. We can express ZDT for all ranks, any delta, in terms of the Derivation modular form. Here you get the eta and eta to the 24. This is some kind of universal factor on how to deal with K surfaces, and that's computed at these values of the modular parameter, evaluated at these values of the modular parameter. So if you look at this expression, it kind of looks a little bit as that it's not exactly a Hecke transform, but it has some flavor of Hecke transform. And that's one of the interesting things, that there is some construction that appears in this cell. Now, so that's one. I'll explain how we derive this and in what sense this is actually proven. I mean, it's proven certain modular, certain assumptions that I'm going to make very clear. And the other thing, but before I go there, let me just also state the modularity properties. So how much time do I have left? Let's try to Okay, thank you.
Yeah,
All right, so, well, the modularity properties of this. Good. So the statement is that if I take the whole collection, so for fixed, so that's 1. Now, 2. So for fixed R, if I take this collection of series with delta in the quotient lambda dual 1 R lambda, this is the vector value modular form for let me just say the weight is it's easy to write, of weight minus 1 minus the rank of lambda over 2. For a certain representation rho lambda r of the metaplectic group. Now, what this representation is, I'm not going to write in detail the formulas, but what it really is, rho lambda r is really the same as the Veil representation for a rescaling of the lattice. So for the lattice square root of r lambda, contained in lambda tensor R. If you just work it out what it is, so you can check. Well, anyway, so that's the statement. That's what we claim. These things form a modular form. So what's funny about this, if you look at this construction a little bit, you try to understand what's happening. What we really did was to start with the vector value modular form with values in this quotient, lambda dual mod lambda. So this here, it's a VVMF, or lambda with values in lambda dual mod lambda. And this construction somehow produces a vector value modular form in a different representation, which is, well, it's the very representation associated to some rescaling of the lattice. So it looks like almost it has some kind of flavor Haeckel transform, but at the same time it's certainly not, because it changes the representation. This is something we'd really like to understand better, and it has any connection with existing constructions for Haeckel transforms at vector value modular. So I should say there are some results. I mean, there are constructions in the literature, in the number theory literature, Haeckel transforms of vector value modular forms, but it's not like this. So perhaps I should add this as a remark, if I have some time. As a remark, there is work of Brunier and Stein who define Haeckel transforms of vector valued modular forms. But first of all, their construction doesn't work for any value, any R. It only works for very special R's, and I forgot what. They're supposed to satisfy certain boundaries properties. So for certain values of R, and at the same time, it looks what they define is something. It's more like a Haeckel transform. It's closer to the standard Haeckel transform, because it takes, it maps vector valued modular forms to vector valued modular forms in the same representation. This one is just, it's imposed. It's imposed by the geometry. Like this comes out of the geometry, and it works for any value of R, but it changes the representation. So we don't really know what this really means. If there is anything deep related to this in a number theoretic sense, we're still thinking about this. But it's certainly going to require some reflection. Try to understand if this is something interesting. I suspect it will have some interesting interpretation in terms of finite covers of modular curves, but we haven't gone with that. There's going to be some geometric interpretation here for this construction that we haven't worked out. In terms of now, okay, so these are the main results. So now I should perhaps say a few words about how we prove them. So because this is a math conference, I'm not gonna probably take bigger questions. Okay, so let me just say, for one, how we got this. Where this follows from. This really follows from work Golampo, Yokinobu Toda, and Artan. So what this follows from, so they use some fairly intricate wall crossing construction. So what they did was from wall crossing. So by wall crossing, you can relate this partition functions we've been looking at, ZBT. Well, better say the invariants themselves, because the partition functions don't occur as so this invariance can be related to vertical PT invariant of X over P1, stable pair invariance, as defined by Canary and Thomas. So there is some fairly very elegant formula they wrote down relating these two partition functions. So again, because probably I have time, I can probably write the formula to just give you an idea what kind of formula they wrote down. Yeah, so it looks something like this. Z is the vertical of x equals, it has some kind of product expansion in terms of this invariance we are looking at. And then there is a second product here. So there is some exponential of something similar that I'm not going to write now. I just wanted to give you the general structure of the formula. So, of course, this formula, when you first see it, it's not by any means clear that this side determines that side. And actually, there is a lot of work, there is a fair amount of work to do to understand how we can actually determine the DT invariance we are interested in from this formula. And this is known, well, it's known it's known explicitly if we grant PT, the correspondence between stable pair invariance and Gromov-Witten invariance, PT Gromov-GW correspondence. So if we grant that, so that's where I'm saying we have to make some assumptions. If we grant this, which is something that I guess nobody in the field doubts, but it hasn't been proven in general, if we grant this, then we can use the explicit results of Maulik and Panda-refunded for vertical Gromov-Witten invariance in this formula. So then we can use Maulik and Panda-refunded for Gromov-Witten vertical. And on top of that, it's not, the work is not done yet because there is some fairly interesting combinatorial structure, and then you need plus some interesting identities, I should say, for coefficients of Jacobi form. So this is something that when I first realized, I mean, this came out of a lot of many computer simulations and whatnot, calculations, and when I just some kind of conjectural identity emerged that was completely, I was mystified. And then Thomas Kreutzig managed to prove it in a few days. Anyway, but he's an expert in Jacobi form, so where I am not. Anyway, so that's what it takes. So we need to use this, and I should say, okay, so we need to use this, and we also have to grant, you have to grant the multi-carbon formula that I wrote down, formula for DT there. Okay, so there are things that are in general widely believed to be true. Certainly nobody doubts them, but they haven't been proven in general. If you accept the statements, then we can extract, then we can prove the formula I wrote down before. In that sense. Now, for this, for proving modularity, this is just it was a hard computation basically. We were stuck for months with this until we discovered an old paper of Montane from the 60s, I think, or 70s, where he writes down a very explicit, not very, it was a very interesting formula for the matrix elements as a pair representation. So there is some work of Shintani, fairly work, which works out the matrix elements of the pair representation. And using that, it took us a long time to discover this paper. As I said, it's from the 60s or the 70s. Using this and hard computation, you can prove this. Because for a very long time we were stuck with this because we were kind of running into all sorts of crazy identities for finite Gaussian sums that I had no idea how to prove. But somehow finding this formula, this formula allowed us to bypass all that, and it was really fairly potent. So that's how you prove modularity. Now, what I wanted to say, I could say a few more words about, depending on how much time I have left, I can say a few more words on the derivation of the main formula. There's an alternative derivation of the main formula, which is based on physics arguments. And it gives you some kind of, it's not rigorous, and you may wonder, why do I even need to think about it? But it gives you a different perspective and different insight in that formula. So I don't know how much time I have left.
We have more than 10 minutes.
10 minutes?
Yeah.
Okay, so I think I can spend maybe 5 minutes, more, a few minutes saying a few words about an alternative derivation of the main formula. Which in fact, somehow, as often is the case, it was the way this formula was first found. And then we realized we could actually extract it from this work of Amin and Okunobu and Monte. But initially, this formula appeared from a totally different way of thinking, which is adiabatic heterotic type 2A duality. So this came from a totally different universe, if you want. So I should say an alternative derivation of the main formula uses adiabatic heterotic type 2A duality. Right? So the idea, to explain the idea, it's coming from physics. Now we started our discussion with a K3 pencil over P1, which had, well, generically smooth. It has some bad fibers once in a while. Looked something like this. So this was my K3 pencil. And then if you think about what you're doing, if you, for example, let's imagine you're studying the problem for stable sheets, not semi-stable. I'm ignoring semi-stable because those can be gotten by using the Monte Carlo formula. So let me just think about this gamma being primitive. So I don't have semi-stable. The charge vector is primitive, the numerical invariants are primitive, so no semi-stables. If you have no semi-stables, then it's easier because you can prove that all stable objects have to be actually scheme theoretically supported on K3 fibers. So you get some kind of fibration structure of the moduli space, roughly speaking, just to give you an idea what happens. So then you can do the computation fiber by fiber, and there is a rigorous way to formulate that using variance constructible functions. So what one can do in this setup is think about, I haven't mentioned it, but I will just say now because it's relevant. There is this alternative way of thinking about Donaldson-Thomas invariants in terms of constructible function. So the dt invariant, in the primitive case, which is, remember, that's integral. So dt of x and gamma can be written as some weighted Euler character of the moduli space of stable sheets relative to some constructible function, which was first discovered by Behrend. And because it's a weighted Euler character, you can do it. You can stratify in any way you want and compute it. So what one can define is you can define local invariants. You can define local invariants. So you can take any point on P1, and what I can do is I call dt of the point in gamma to be just the Euler character of omega m omega of the point in gamma relative to the same constructible function. But this is just the closed subspace consisting of all sheaves supported on, so this is sheaves, it's moduli of sheaves supported on XP, on that particular fiber. So I can break the problem into a fiber by fiber computation. Of course, if you now think of what happens for smooth fibers, the problem was solved with computation. The counting was done by, as I said, by Amin and Monte. So you can use that for small fibers. But then the question is, what happens when you hit the singular fibers? So that's when the problem gets hard, because for singular fibers, almost nothing is known. At least I couldn't find much in the mathematics literature about moduli spaces as torsion-free sheaves on no K3 surfaces. Nothing to the extent that I would be able to actually compute their Poincare polynomial, for example, or something like that. So then you hit this problem, but that's where physics comes in and says, well, okay, let's see, by this duality statement, if we use heterotic type 2A duality, I can think of this, roughly speaking, a family of K3 surfaces as a family of smooth heterotic conformal field theories. So for each point here, we associate a smooth heterotic conformal field theory. So, which means I have a Berkeley operator algebra. I should say on T4, whatever it means. which means I'm looking at the heterodic compactification on T4. The target space is T4 times R6, it's not R10. So I should say T4 times R6 to make it clear what's slightly clear what I mean. So you associate the smooth heterodic CFT. So then it turns out that counting sheaves on each fiber is equivalent to counting certain perturbative states there. And then once I'm here, I know how to do the count, because that's right. So counting sheaves on each fiber, it becomes equivalent to counting the so-called the Volcker-Harvey states in heterodic theories, which is a known exercise for string theories. It's a fairly simple exercise. So so counting sheaves on XP now becomes equivalent to counting basically heterodic BPS states. And this is something that was done by physicists. In particular, there's a paper of the Volcker, Greg Moore, Piolin, and Denef, which does this in great generality, so we can use Denef, Moore, and Piolin, there's some work that does this in a great generality, so we can borrow their results and get predictions for the count for this particular local invariant. We get physics predictions for those invariants. And in particular, you get predictions for the guys associated with the singular fibers as well, because the cool thing about the duality is that it replaces nodal fibers still by smooth heterodic CFT. So I don't have any problem. And from this point, I don't care I don't really care much if I look at a singular fiber or a smooth fiber, aside from some subtle points related to discrete gauge symmetries, which are important, but they are easily understood in physics terms. So overall, you can extract, so the physics story will give you predictions, explicit predictions for all these local invariants. And in fact, it can give you more. If you want, you can get predictions for any singular fibers. I mean, by which I mean I can allow any kind of AD singularities on the singular fiber, not just nodes. I can do any kind of AD singularities. So I get some predictions like this, and then the issue is to put them together to sum up and do some kind of integration, because that's what you're doing here, and get the global invariant, and that's some computation that has to use some properties of the Nether-Lefschetz loci, and you get that formula. So that's really how that formula was initially found. And then eventually, we realized we can actually almost rigorously prove it using this work of Eichmann and collaborators. So I think now it's a good time to stop. I mean, if I have any questions, I can. Thank you very much.
Modularity clear from physics argument?
No, because the modularity is not totally clear from physics arguments, because this is done fiber by fiber, and modularity is something that comes, modularity uses the properties of the Nether-Lefschetz loci in an essential way. So modularity is a property of the global thing, not just. I mean, fiber by fiber you have some modularity, but that's it's clear and it's simple. It's a modularity of 1 over eta to the 24 basically. But that's not the interesting modularity. The interesting is when everything is put together and you get this vector-vector modular forms.
Could you say a few more words how the nodes of the K3 pencil affect the harmonic side?
Well, they don't affect much. I mean, I'm going to have to use all sorts of physics language. The point is, you're doing, the heterodic CFT is totally smooth. So you can do basically the same count as you did for the smooth fibers. The only change is that if you think of, there is some kind of non-abelian gauge symmetry enhancement associated with the node. So the heterodic gauge group in 6 dimensions jumps from an abelian group to SU2 or something abelian. And SU2 has a obviously non-trivial Weyl group. So then you have to identify. So that Weyl group is a gauge symmetry. So you have to really identify certain states. So in order to avoid multiple over counting. So basically what you're doing is that you take some kind of, you take the counting you did here and you mod it out by some discrete symmetry. That's what I'm saying. That's what happens in a nutshell. But that discrete symmetry is well understood. You understand very well how it acts on the spectrum, and then you just take the invariance. That's the only change. So that comes very naturally.
It's a global symmetry.
It's in space-time. It's a global symmetry of the CFT. In space-time, it looks like a gauge symmetry because that's why you identify. Is you have to identify gauge equivalent physical states. So yeah, that's how you get it, and everything in the end matches perfectly, and you get that close formula.
So in the model where you went to the double cover,
yes,
the small resolution,
yeah.
What's going to depend on whether that's projective or not?
Oh, there is I learned this from you actually. There is some mathematicians work this out, right? You know when you can globally construct a projective solution. I forgot. I think in this case you almost can never do it, right? Because you don't satisfy those homology relations that you need.
But that does not affect your
No, because you get a holomorphic family of algebraic surfaces. Each surface is projective. Just the way they fit together is not algebraic. But it's still holomorphic. So then, that's my understanding. So you still have a map from the sigma, the base, to the moduli space of lattice polarized KV surface. You still get the well-defined map, even though the global total space of the pencil is not projected. But that, at least Mallory and the Pandari don't seem to be bothered, and they just get the map and they find the Nether-Lefschetz numbers from looking at intersections with the Nether-Lefschetz divisors. I think in this case probably that's almost never projected because you can't satisfy the relations you need to satisfy among exceptional curves. Like there is some, I learned from you some relations in homology that you need to satisfy to be able to.
Oh, Friedman.
Yeah. No, but when going. Yeah, that's right. Yeah. No, we don't need. Yeah, we don't really need that. No, we don't need that. It's just the fact that each fiber is still projected that counts in order to define it.
So the Jacobi form identities you were talking about, where does the Jacobi form fit into the?
Oh, it comes from. Of course, you did a lot of work on that, right? It really comes from when Mallory and Pandari found a closed formula for the vertical GB invariance, Bottom-Buffer invariance of a KV pencil. And that was written in terms of the Jacobi form.
So it's that.
It's that Jacobi form, but the thing is new, at least new to us, and we never found it, is some completely, apparently crazy identity among its coefficients. Apparently wasn't known even to experts because they had no reason to look at such a crazy identity. So basically it's a relation between, at the end it's a relation between genus 0 GB invariance and higher genus GB invariance of the KV pencil. Vertical. So there's no relation there. When I first found, I really found it by doing computer computations until I found that look, everything was matching with, except that I got this relation and I checked it numerically. And then, well, I asked my collaborators and Thomas proved it. He found a way to prove it, which is amazing. I still don't know how he did it, but it was pretty amazing how things click at that point. Yeah, I should say, this work is certainly, you did a lot of work on KV pencils. Sheldon, and it's when I say it could be there could be follow-ups that because we were thinking that there could be some refinement of the whole story that relates these invariants to your refined invariants. So yeah, so that's something again we have to think about.
So singular fiber interpretation in terms of representation theory.
Yeah.
Can't actually character or representation
what I can tell you is the moduli space of CFTs, you can think of it as some Grassmannian. Okay, you have a Grassmannian of space like four-dimensional planes in R4, R4, modeled out by some discrete group, by some arithmetic group. Now, the singular fiber, what happens to the singular fiber is that this plane that you're classifying, the plane, the foreplane, will have a special position so it intersects, it picks up points on in the ladder. right? And generically, it won't have any points in the lattice. And then generically, physicists say there is only a billion gauge symmetry. But if you pick up points in the lattice sitting in that plane, then you suddenly get nanobillion gauge symmetry, depending on how, if you pick up some roots of some AD gauge group sitting in this plane somehow, then you get that group it becomes a gauge group, and then its file group it looks like a discrete gauge group. So you have to model out by this discrete symmetry. I mean that's roughly what happens. Yeah, the enhanced gauge symmetry in space-time, but if you look at the file group of that gauge group, it's just going to be some finite group that acts on the heterotic states. And then what I'm saying is that I need to take only the invariant part of the spectrum. And then everything, of course, it's going to act on all the characters you want in the CFD, and then you're going to break on the same characters, the affine algebra, and it's going to be broken into representations of the finite group and everything.
But before that, you relate to the invariance of the system delta function?
Oh, no, yeah, well, that was, we just used that in the proof of modularity. I don't see any connection with the heterotic thing.
Because you said that function on first in terms of modular representation.
Well, the part of his work we actually use, it's a very nice, very beautiful formula for the matrix elements of the file representation. That's what we use. It has a very, very cool formula for that. And it turned out to be tailor-made for what we needed. It allowed us to bypass some crazy stuff about finite Gaussian sums that we couldn't figure out. But I don't see any connection directly here. I don't.
Any more questions? Okay, thank you.